So here we go. Hello everyone and good evening from Egypt. This is me again, Assam Helmi, a success partner with OBA Energy. I'm very happy to be your moderator today in this webinar number 64 provided by OBA Energy. This is a series of free webinars that we provide uh, frequently, you can say on a weekly basis. Today's webinar is titled Basic Concepts of Water Flooding, a very interesting topic and session webinar today to discuss with our guest speaker, Engineer Islam Fawaz. As you, some of you have may attended with us before, we have a typical presentation that we made in the start of our webinar, which is OBA services plan. I will not be too long in this webinar. I'll try to make it short as possible as I can. In front of you now, you see our dashboard. In terms of numbers, we as OBA Energy, we have more than 40 instructors in different areas of experience. We have already provided a lot of live courses. We exceeded 30 live courses in different topics, and numbers here in this dashboard actually is not updated, as I just mentioned that we reached to the free webinar number 64. We provide a lot of services, actually, not only courses, we also provide mentorship programs uh, and technical studies for companies and many other interesting services. On the right bottom of my screen, you can see that we already reached to many countries all over the world. So we have audience from almost all over the world. I'm not talking here about numbers of attendees, but I'm talking that we could manage to reach to these areas through our marketing campaigns. So what's next? Yeah, our eighth quarter live courses plan, which is very interesting plan in the upcoming 2 months. We have 4 interesting courses, starting by one of the most interesting topics that we have webinar about today, which is water flooding design and optimization. This course will take place in the 13th of May and will last till the 18th of May. We have more 3 interesting courses: gas lift theory and operation and design, which will start in the 27th of May and end by the 1st of June. 2 more courses, advanced integrated formation evaluation, that will take place in the 10th of June and end by the 15th of June. The last course, which is a very interesting and dynamic course, which when it comes to the well operations, very interesting to know about these courses. Advanced well intervention operations, which will take place in the 24th of June and end by the 29th of June. And as you can see here in the black color, we have break days during these courses, which is almost Tuesdays. You can register in one or more of these courses through scanning this QR code that is in front of you now. And I will also share a direct link in the chat box that you can use to register in these courses and in other services that we provide, like recorded courses or mentorship programs. You can see now the link for these services in the chat box area. As I mentioned, we have a track record of recorded courses that were live on some dates. These courses, this list, by the way, is updated than the ones that I presented in previous webinars. We have now 26 recorded courses available through our website for you to register in. You can see that we added updated courses here: introduction to data analysis, perforation design, rigless well intervention, ESB hand and software design, and many interesting other courses in different softwares that are used in the energy industry, like OFM, FracCAD, Sapphire, GAV, PipeSim, TechLog, Petrel, all interesting softwares that are the most used in the oil and gas industry. Also, you can use this QR code to scan if you would like to purchase one or more of these recorded courses. And the more you purchase courses, the big the sales that you get, the big the discounts that we will provide to you. I also mentioned that we have mentorship programs. This mentorship program is actually uh, you as the mentee and as OBA Energy, we designed this program together to meet your needs in terms of the knowledge that you want to get, and also um, based on your free times, and everything is designed on your preference. Here's a screenshot from our webinars. I'd like also to encourage you to pay a visit to this website. You will find very interesting stuff on it. As I mentioned, that our recorded courses is available on this website. You can see this in the screenshot in front of you now. Uh, we also provide internship programs for, we have already conducted 2 ground internship programs for different group of students from Lebanon, like Beirut Arab University, that came here to Egypt and attended very interesting site visits. As you see in this gallery, uh, actually lovely pictures in this gallery. You can become one of our ambassadors by joining us in any of these services that I mentioned, whether internship, recorded courses, live courses, mentorship program. Uh, and once you become an OBA ambassador, you join our community and you enjoy the knowledge that we share with you privately, and a lot of discounts that we provide for our ambassadors as well. Um, Sorry for being too long. I'd like to mention some rules before starting this webinar. Please note that I have muted your microphone to make sure that everyone here in the meeting got the point clearly without any intervention from others. Also, please don't open your camera to make it clear for others. If you have a question during the webinar, please put your question in the chat box, and I will be happy to say your question and read it loud to our instructor and our guest speaker today to answer your question clearly. Uh, one more note before starting is that if you joined us using a name like iPhone Galaxy or something like this, please go rename yourself with your full name, as we will be sending certificates of attendance for today's webinar through our email in 1 week. So thank you. I would like now to introduce our guest speaker for today's webinar, Engineer Islam Fawaz. Engineer Islam is a senior reservoir engineer with more than 12 years of experience at GAPCO, Gulf of Suez Petroleum Company here in Egypt, and he has a demonstrated history of adding value through field evaluation and asset management. Mainly tasked with looking after offshore fields here in Egypt in Gulf of Suez and field development plans. He's a highly skilled in field development, water flooding, which are our topic today, reservoir simulation, reservoir management, and a leading high performance team. Engineer Islam, thanks for joining us today. And I'd like also to mention that this is not the first time for Engineer Islam to join us in these webinars. Engineer Islam has already conducted one of the webinars, which is available through our YouTube channels. And I also like to encourage you to go to YouTube. If you missed any of these 64 webinars, you will find it recorded on our YouTube. Engineer Islam, thanks again for joining us today. The mic is yours to start the session now.
Thank you, Assam, for your introduction, and thank you all for joining our webinar today. So let's start. I will share my screen. So give me access. Yeah. Everyone can see my screen?
Yes.
Yes, okay. Thank you, Assam, and welcome to our webinar today regarding the basic concept of water flooding. So our agenda for our webinar today was to start. We will start with introduction about what's meant by water flooding and what's kind of water flooding pattern, and also we'll go through water flooding pattern methods in water flooding, and also we'll discuss some of the geological aspect of the water flooding, and finally we'll go through the role of surveillance plot in managing the water flooding project. So let's start by introduction. I would like to emphasize in this point, this is hypothesis. The characteristic of any reservoir can be inferred from analyzing production and injection data. And also most of water flooding project falling below our expectation due to lack of the geological data or lack of understanding the geological aspect of the water flooding. So this point is very, very important when you are working with water flooding project. And also, we'll go through what is the type of recovery. We have many stages for the recovery of the field, starting by primary recovery. The primary recovery, which means the first oil is coming to the surface by the natural energy that the reservoir has. After that primary recovery, we implement secondary recovery, and this method is mainly to apply artificial pressure into the reservoir in order to maximize the production from the reservoir by like water flooding and pressure maintenance. And also by then we'll go to tertiary recovery. So we are looking after the primary recovery and secondary recovery. We're looking for the left oil behind, and we need to maximize the recovery up to from 50 to up to 80% recovery factor due to the sum of the enhanced oil recovery that you made in your reservoir. So improved oil recovery is a combination of secondary recovery and tertiary recovery, but EUR is a tertiary recovery and only targeting the immobile oil in the reservoir. So for the conventional recovery targeting the mobile oil from secondary recovery up to tertiary recovery, but EUR is targeting the immobile oil from the reservoir. So what is the water flooding cycle? Water flooding cycle starting from producing oil and water at the surface, and after producing the oil and water on the surface, we go into the production facilities. From the production facilities, we separated oil and water. Some of water go to disposal, and some of water going to the water treatment. After that, from the water treatment, we have two sources of water coming from the well or coming from any kind of water, like from the dump flood, from the water flood facilities, or coming from the reservoir, aquifer, or from dump flood fields. This water going to water treatment in order to make sure the water injected into the reservoir is very clear. After that, the water injecting the water to the facility, injection the water to the well in order to post up the reservoir pressure and maximize the recovery from the field. Then the water go to the reservoir. This is a closed cycle, and this mainly tasked by mainly disciplines. Don't work in your island. So water flooding is multidiscipline, multitasks engineer, starting from the geoscience team, starting from the resource progression team, which is combined, this asset team combine geoscience, combine geophysics, reservoir engineer, petroleum engineer, and facilities engineer. So before we go into water flooding project, you have to keep this concept in your mind. From the geoscience, we define the structure framework of the reservoir, and from the geologist define how many rock types you have, what is the fishes distributed in the reservoir, and the petrophysics defining how many rock types that you have, how many flow units, what is the donation, is the sand is continuous in the reservoir or not. After that, the water and the fluid is producing to the surface here. After producing the fluid to the surface here, you have to treat this kind of the fluid, because this kind of fluid, some HSE issues, we have to going to this water to the facilities in order to remove the unwanted material, that because we are going to re-inject again this into the reservoir. So the production engineer handling this point, and also the production chemistry handling this point. After that, the water is coming and the injection back to the reservoir. So you have here to make sure the injected water is very clear, because if we have uncleared water, the uncleared water maybe blocks the perforation, and your water flood project end at the finally end which in vain, and will lose the injection from your reservoir. So I would like to mention that, and the main message from this slide, don't work in your island because everything is communicated, and share your knowledge with your team in order to maximize the benefit from the water flooding project. So as we are working through the water flooding project, we come across different challenges in your water flooding project. So we come across starting from the facilities constraint. This is very important. After we have the fluid and the surface, you are setting in some concept in your mind according to the pattern balancing, how to define the pattern in your reservoir. After we define the pattern, we will inject the water. During the injection, you have to keep in your mind, you have to avoid the early water breakthrough, because early water breakthrough will affect the recovery factor from the field. Then the water will cycling from the wells, and after that, you have to keep your eye how to maximize and improve the sweeping efficiency. This is the effective monitoring and surveillance schematic required in order to maximize the benefit from the recovery factor. So when you ask you questions, what is the recovery factor? What is the recovery factor? What is the water flooding about? The water flooding is about two concepts. One is the pressure maintenance. You have to supply the reservoir or post up the reservoir pressure in your field in order to push the oil towards the producer. And also this is managed by production of take and injection volume balance. This is what I will show you in the next slide, which is called VRR, voidage replacement ratio. And also you have to keep your eye in sweeping improvement, because the reservoir is not unique. So we have different high perm streak, or we have low permeability streak and high perm streak, or we have fast. So you have to keep your eye how to maximize the recovery by improving the vertical sweeping efficiency. Like in this graph, we have high perm streak. Once we inject water, the water will propagate through the high perm streak and reach up the producers. By then, the water will pack pressure the oil in the lower intervals here, so by end up finally by low recovery factor. So you have to keep your eye how to maximize the vertical and the area sweeping efficiency. You need to inject more than 1 bore volume or 2 bore volume in order to get the required water flooding or the maximum recovery from this field. So those two important points you have to keep your eye when you design the water flooding project. So the fundamental of the water flooding here, as you see in this graph, once we have a core from the reservoir, just a core is 1 inch by 1 inch, and we apply the scale data and the fraction flow curve. This is a fraction flow curve, or the displacement mechanism is described how the flood or the saturation progressed with your reservoir. So if we're looking for this graph, we have the saturation at x-axis and we have the fraction flow. From this fraction flow, we can define from the tangent here the water saturation at the flood front or at the choke wave. As you can see here, this is the in the top right picture. This is the average water saturation at the water front or the choke wave. Behind that, this is the average saturation is behind the front. And so once we are working here with water flooding, here we have 3 regions of the water flooding. One is called the water bank here, and the water bank here, which is the area around the well here. And after that, we have oil bank. You have to push this oil to be produced from the producer. And also we have another region which is unaffected by the reservoir. Some we have free gases in this reservoir. So you have to design how to push this oil, how to maximize the recovery, how to support this unaffected region. So that's why you are going to pattern or infill injector at the middle of the reservoir. So this is the fundamental concept is based on the pore scale displacement. This is just only at the bore scale level, which is 1 inch by 1 inch. Okay. So the recovery factor, as I mean, from all of us, we know the recovery factor is the cum oil divided by the oil origin in place. So in water flooding, what is the oil origin in place? So before we getting to answer this question, you have to understand what is the difference between net pay or floodable pay. As you can see here from this picture, this is not floodable base. The bottom interval here, so I will check the reserve point. the bottom interval here is not communicated with this interval. This is not is a net pay, but is not floodable bay. This interval sometimes could be communicated or not. This interval is not communicated. This is not floodable bay. So you have to answer this question. The OYEB, you have, once you say this is OYEB, so you have to consider for water flooding the floodable bay, not the net bay thickness. So you have to define this interval or not. So as you see here, this injector here, once we inject here from this interval, and this interval should be in this layer, the injection are communicated, but in this layer not communicated with the producer. Okay, this is the not floodable bay and the net bay. So when you're talking about communication, we have different level of communication. If we have too much communication, like we have safe zone, so we have many definition for this. We have too much communication, like we have safe zone. Once we inject water, the water will cycling from the nearby producers and will live with this. So you have to understand this point. If we have neutral communication, we have communication in the reservoir, or we have continuity in the sand. How to define this is a continuity from the geological prospect, from the geological work. So you have to going to pick every structure point here, and we see your correlation. Is this sand is continuous in the reservoir or not, and something like this. If we have any baffle between this injector and the producer, we have a communication, but this is a too little communication. How to quantify this? Once you are working in your data and you have the pressure and the production data, so you can quantify if this is fully communicated or we have a baffle between this producer and this injector and so on. So let's go to the another topic. What is water flooding pattern? What is mean by pattern? As I said in the first slide, water flooding, we have two metric for the water flooding. One is post-up the reservoir pressure to maximize the recovery from the field. That's called pressure maintenance or pressure support. The another one you have to keep your eye is the sweeping efficiency. How to maximize the recovery factor from this field by looking for through pillar. One, which is the displacement efficiency. What is mean by displacement efficiency? This is coming from the fraction flow at the pore scale level. Once we have the fraction flow and the relative permeability curve from the pore scale displacement, you can define what is the typical recovery factor at the pore scale level. But you are working in a reservoir with kilometers. So this is not the ultimate recovery. This is the ultimate recovery factor from the field if we push every barrel oil from the reservoir. But the reservoir is not homogeneous as you expect. So you have to look for the vertical sweeping efficiency if we have high perm streak in the middle, or you have to look the aerial sweeping efficiency due to the compartmentalization, or we have a baffle, or you have very heterogeneous reservoir. All of those metrics you have to look up at this in order to get the maximum recovery from this field. This is another metrics for the water flooding. That's why we have water flooding pattern. Pattern, what is mean by pattern? Here we have different pattern from the field, starting every project starting with peripheral water flooding pattern, peripheral injector. As you see here, the injector adds the periphery of the reservoir in order to push the oil toward the producer and maximize the recovery from the field. But in case if we have a low permeability reservoir, this is not work well. So you have to go to another pattern, if we call regular pattern, like 5 spot, 7 spot, 9 spot, and line drive or staggered line drive, as we'll show you on the next slide. Or we have very heterogeneous reservoir, or you have baffles in between. We have a regular pattern or combination from the peripheral pattern or regular pattern. That's why this is something like this. We have 3 regions. Each region we have 1 injector in order to boost up pressure for this region, boost up pressure for this region, and the boost up pressure for this region. So every reservoir could not be have one unique solution. We have different kind of the pattern, and you have to play with every pattern. How to define this? From running simulation model and find which pattern is good. We have many sensitivities for the which pattern will spacing, will pattern, and something like this. So you have to design for each one is the best for your reservoir. So water flooding, what is the best pattern? As I said, so you have to consider in your mind how many producer, how many injector, what is the well spacing and the orientation for your reservoir. What is mean by orientation? If your reservoir has a preferential directional permeabilities, you have to design this point. If you have a preferential direction in northeast, you have don't inject in this direction. You have to inject from another direction in order to avoid early water breakthrough. And also the completion design. If we have, this is what's called the conformance review. Completion design, which is mean if we have a high berm streak, you have to avoid the early water breakthrough by don't perforate it, or you have to dual completion, and we have between dual completion one produced for the fast zone and the other produced for the low berm zone. So you have to design for this point how to maximize the recovery, how to deal with kind of the issue. What is called conformance review in your reservoir. So the criteria for setting which one is the best is depend on something like it's depend on reservoir continuity in terms of vertical. Is your reservoir continue in the vertical direction or aerial direction? Also, if your reservoir is heterogeneous, you have to consider this point in your design. If your reservoir have your anisotropy, and every reservoir is anisotropics, and the rock and the flow properties, you have to keep this in your mind, and the structure of this reservoir. As you see here, this is the kind type of the pattern here. Like we have 5 spot, and we have direct line, and we have a staggered line. Staggered line, direct line, which is mean each producer is, we have one injector for each producer, one injector for each producer. If you put the injector in the half distance between two producers, this is called the staggered line. This is 7 spot, this is peripheral, and this is inverted 7 spot, and so on. So for, let's start by 5 spot pattern. The 5 spot pattern, the normal pattern, the producer in the middle, injector is at the outer here. We have spacing which is 640 acres, and we have one injector, one injector, one injector, and one injector, and one producer in the middle here. And this is called 5 spot. Sorry, it's called 5 spot pattern here. One injector, and we have 4 producers. This is called 5 spot. How many producer and how many injector? Actually, we have 4 producer, but this 4 producer have a water or have support from this injector, and also have support from the injector, have support from another injector, like something like this. This, for example, this producer have support from 4 injector. So every injector is contributor with 25%. So we have 25%, 25%, 25%, 25%, and one producer, which is mean we have one injector, one producer. So this pattern is a square. What is space is equal. So you have to design this in your simulation model, which pattern is equal. You have make sensitivities, what is the well spacing is optimum in order to get the maximum from this field. And also the displacement efficiency for this 5 spot is very high. And also we have this kind is called 7 spot pattern, and we have normal pattern. Normal, which is mean the producer in the middle. Inverted, which is mean the injector in the middle. So the injection and the production ratio, as I said in the previous one, how many injector here? We have 1, 2, 3, 4 is contributing by 25%, and this with 50%. And also we have at the end, we have 2 injector and we have 1 producer. For the inverted, we have the opposite one. So this is also, you can down space by shutting one of 2 the injector. It's easy to down space for a spot, for a spot, which is mean we have 1 producer and 1 injector here. 1, 1, 1, 2, 3, 4. Everyone contributed with 25. So we have 1 injector and 1 producer. So let's keep 7 spot in your mind by chicken wire in your you have chicken hen here. This is called the chicken wire pattern, and this is like that you have, everyone have this kind, so you remember this with 7 spot. Also for the 9 spot here, and the injection to production ratio is 3 producer to 1 injector. This is a normal here, and the pattern is a square, and also its placement is high and easily down space to 5 spot, and the 5 spot also easily to down space to line drive or staggered line drive. And also line drive mechanism is a direct line drive, which is mean every injector is targeting 1 producer. this injector targeting this producer, this injector targeting this producer. This is called direct line drive. But if the injector in the middle between two producers, this is called staggered line drive, because the injector is targeting two producers, not only one producer. So this is the difference between line drive and the staggered line drive. I know everyone in your mind now. Yes, I know we have different type of patterns. So what is the optimum one? The optimum one is dependent on not only technical, is dependent on some perspective in your mind. The best pattern is dependent on what is the goal of water flooding. If your goal in water flooding is to re-energize the reservoir system and sweeping the oil from injector to the producer, this is your goal. But what is the best pattern to allow much injection as possible as you can into the reservoir? So you have to keep in your mind the integration chart. What is the capacity or the equipment capacity in your field? You have what is the maximum water supply. If we have 13 MPD water supply, you cannot apply with any kind of pattern. What is if you have rate and pressure limitation in your field? The economics could be the 5 spot is the best one, but our economics the best one from the technical point of view, not from the economic point of view. So this is mainly depend on some factors, and this just your role is to define from your model which pattern is the best in terms of technically and terms of economics. So this is the answer to these questions here. Also, when you are working here, you have to keep in your mind two important points: the mobility ratio in your reservoir. Mobility ratio is the volume, is the mobility of displaced phase over the displacing phase. We have displaced water. This is mobility of displaced water to the mobility of displaced oil, which is termed by and which is the mobility ratio. If your mobility ratio is the one, which is mean we have piston-like displacement. What we are inject, we are produced. And the choke wave or the water front is moving steadily in your reservoir. This is the best way to get the maximum from the reservoir. But in case if we have high perm streak or we have unfavorable mobility ratio by we are injecting with higher rate, let's lead something in a fingering or finally to unswept oil. And also this will water cycling from this reservoir. So mobility ratio above 1 is unfavorable. And also when you ask you questions, what is the best time to start water injection? The best time to start water injection is at the bubble point of pressure. Why? Because if we're looking for the viscosity and if we're looking to the pressure here, this is the point at the bubble point pressure. This is the maximum volume at the bubble point pressure, and the gas is not liberated from the reservoir, because if we have a gas in the reservoir, the gas we have very compressible. You are injecting, but you are not see any response because the gas is highly compressible. So the best point is at the bubble point pressure, or from if you have asphaltenic crude oil, the best operating point is at the onset of asphaltenic pressure. Okay. Another factor will affect the selecting the optimum time here, the porosity, permeability, saturation. All of this in terms of reservoir properties and the flow properties are very important when we defining the optimum time for starting and when you're designing the water flooding project. So let's go to the method of water flooding pattern. As I said in the first slide, or the triangle here, which is indicated for injector, and the square here, which is open dots here, this is indicated for a producer. And this line between injector and this line is called theoretically non-flow boundaries. And because when you are designing a pattern, you assume that no flow boundaries here, any flow doesn't come across these boundaries. Okay. So regular pattern have producer in the middle, inverted pattern have injector in the middle. Okay. So when you're saying this boundary, this is the pressure boundary, no flow boundary, and this you assume in your mind, or this pattern, any fluid doesn't come across, or any fluid doesn't come across this pattern from the producer or from the injector. But sometimes you have to deal with a irregular pattern in real field. You have to draw this as a pattern here, and this is injector, and this is the producer. So the reservoir engineer is still, we need to define the pattern by drawing this boundary polygon, but is as a fixed well. If we increasing the number of the well, or you increasing the offtake from this reservoir, this pattern will be changed. Why change it? Because we're changing the dynamic in the reservoir. So this is very difficult when you're defining this. Don't deal with the pattern as a fixed. The pattern is not a fixed. This no flow pressure boundary. If we assuming we have constant production from the nearby producer, this is not constant. Okay. So as I said, when you are dealing with any kind of the pattern or any kind of the polygon, we have two metrics. One is the recovery factor, which is the volume of oil produced divided by original oil in place pattern. So this in order to define the sweeping efficiency, how much you are swept oil from this reservoir, and this is reflected on the recovery factor. But in case you have to pressure support, and this is another metrics, pair pattern voidage replacement. This is reflect the pressure support for your reservoir. The volume inject like mass balance. The volume inject divided by the volume produced. This is the called VRR. So in this point, you are assuming the pattern is constant. What we are injecting in this pattern is constant, and any fluid doesn't come across this kind of the boundaries. So you have to quantify how much flow coming from the injector to the producer, and how each injector contribute to each well in your reservoir. So how you define this point? The best approach is by running streamline calculation to quantify the contribution from the injector to the producer. So this is the input from streamline, like we have rates, well location, flow data, pressure data, flow data, perforation, and also we have BVT data and distributed zero feed run streamline. So solve a streamline by flowing path. This flowing path, which is mean the water, this is the easiest way from this injector to the producer. We have this injector is communicated with this producer, and also we have some sort of communication here, and we have less communication here, and we have a communication here. So you have to quantify the well allocation factor by drawing or the collapse is this kind of a streamline into well pairs like flux pattern map from this injector. How much this producer production coming due to support from this injector. For this example, we have 30%, we have 20%, we have 7%. So this injector is contributed to this producer by 30%, which is mean we have little communication with this injector. But this one is the highest communication. This one is the highest communication, which is means those two producers are highly communicated with kind of injector. This one is less communicated with the injector. So how to define this? From running a streamline, and by the end you have to run flux pattern map, and to see for your manager we have well allocation factor due to the injector in your fields. So myth number one, as I said, pattern are fixed or not fixed. The pattern is not fixed because the pattern change with time here due to a change in the well rate or due to change in the dynamic in your reservoir, shutting producer or open another producer or down spacing the field by drilling and fill well. This is will change the pattern here. As you see here from for Jan 2018 here, this is the injector. We have injector is communicated to this kind of the producer with 66%. But in case if we open another will be behind this, which is means the contribution will change. This is change from 32. We have 15%, we have 7%, because we are distracting the fluid mechanism in your reservoir, distracting the water flow in your, sorry? Water flow in your reservoir. Okay. After 6 months here, You are open another inject another producers here, and you showing this producer with 1% here, and you open another production here from this field, which is mean changing the injection allocation factor over time is associated with an injection of the producer over time, as determined by a streamline and spacing and displace and as displayed by using a flux pattern map in order to display how much injection contributed to each producers. So for the pressure, for the miss number 2, the volume in and out from this pattern. This is when you are working with geometrical pattern, which is mean this is a geometry of the pattern here. If we're drawing this is a geometry, and this is a kind of geometry here. You're assuming in your mind this geometry is a constant through all over the field, but actually is not a constant. Is it just as a guessing game? This is not a constant. Is a change with time. You change the offtake and just reservoir. So those two metrics you have to keep in your mind: recovery factor and the VRR for each pattern. So the volume of the oil this is produced from the pattern is unknown, divided by original oil in place. We have some uncertainty for this point. But for VRR, the volume injected also is unknown. You are injected at the surface, not, and I will show in the at the end of this slides how to make sure the injected water is going to your place, and the volume producing from the pattern is unknown because you assume this pattern is constant, but actually we have some pressure sink away from this pattern here, leading to changes this kind of the pattern. So another one, the oil of the pattern is unknown. No, because you are not starting the injection from the day one. After we have it, depletion in the reservoir with changing, or we have some water breakthrough, or the reservoir getting below the bubble point of pressure, so the OYEB is changing. Yes, because we have different change, we have different flat front or different water saturation. For some area we have increasing water saturation. You don't know what is the real oil contact or not to define the contact is a constant line. You cannot define this because we have it some changing in the multi-phase flow in the reservoir. So we have uncertainties for this point, but you are working with this kind of uncertainties. That's why we need to have B10, B50, and B90. So the recovery factor is a volume produced, as I said, divided by the original oil in place in the pattern here. Those 2 points is unknown. So I wanted to tell you the message of the fixed pattern here. Pattern are not fixed over the time. You have to run a streamline to quantify. If it's not possible, you have to calculate. If you don't have a streamline, you have to calculate the volume and the monitoring this with the surveillance data. And the OYEB of the fixed pattern is generally unknown. So computing the recovery factor and the VRR for fixed pattern is a guessing game at the best. Okay, this is my message from the previous slide. And also we'll go to geological aspect of the water flooding here. For the geological aspect of the water flooding here, if we have stratified reservoirs, which is mean hypermestric, and you have low permeability, high permeability zones, so you have to keep in your mind how to handle this kind. How to handle this kind if we have a fast zone in the middle of this reservoir, the high permeability zone. Once you inject, the water will pump it off from the producer, and we are recycling water. So this lead to vertical sweeping efficiency is very poor, and also the aerial sweeping is very poor. So how to get the maximum from this point? By putting a polymer or cement squeeze, or design it from the completion strategy, or don't perforate the high permeability zone, just perforate the low permeability zone. Avoid perforating the fastest zone. This is what's called conformance. So in your team, you're holding a conformance review. Why conformance review? To get the maximum from this field, and to how to improve the vertical and the aerial sweeping efficiency for your reservoir. Also, for the gravity segregations here, once we inject here, ideally the sweeping is the sweeping should be get uniform here, but the water is slumping because the high permeability is at the bottom here. So once you inject with the gravity, the water will slumping, leading to maximize the production from the leading to the water will slump down here, and the water will break through at the bottom, which is a very favorable here. So you can get this point in your mind when you are putting a perforation strategy for your reservoir. And finally, we'll go to the role of the surveillance in water flooding management, which is very, very important for in order to get the maximum from your reservoir here. So the challenges here when you are working for this kind here, everyone is focused for the well and forget to look at the field performance because well here is looking for the water is pumping out from the reservoir or just going to the injector and seeing if there is no injection from the field, well, could be this interval is plugged by scale around the well and something like this. So the surveillance is very, very important, and you have don't forget to look for your reservoir from different kind of perspective, starting from the field perspective, till block, pattern, and well. And I have gathered this kind of all of the surveillance which is available for the water flooding in order to get the maximum from this field. So before we starting water flooding project, you have to start to look at the field perspective first, and then drill down to the well perspective, because every piece of the puzzle will help you to understand, and the more closer you to answer the question for your reservoir field or for your field, is the more closer to understand what is the conformance, the optimum conformance, in order to get the most of your reservoir. So surveillance is a very, very important, and I have gathered for you the most common 5 plot to show the biggest picture at the field. One is the rate versus time production. Second is oil rate versus cumulative. Recovery factor versus injected pore volume, as I said in the previous slide. Voidage replacement ratio, and cumulative production and the cumulative field injection. So let's start by this kind of example here. For the field, at the field level, the goal is to understand the reservoir at all, knowing the history of the reservoir, leading to know the current state and the production and the prediction for the future in your reservoir. So every question is for you have to answer is to help you to see the big picture for your reservoir. For example, what was the field discovery? What was the development plan for the field? Was the acreage drilled at once development, or did drilling expand from a central area, like we have drilled from the central and then expanded the drilling as a appraising the reservoir? We have down spacing from the reservoir or not? What is the historical rate? What is the pressure data? What is the production data? So you have to answer this kind of questions. So for this field here, this is oil rate, this is the number of wells, this is the water production, this is the GOR, this is the water injection rate. This field is covered in 1946, and if you show here, you have a peak of the production here, and also you have a decline in this oil rate. With this decline, we have increasing in the gas oil ratio. So the gas oil ratio is a good gauge to show you if your reservoir is above the bubble point pressure or below the bubble point pressure. So you can see here the increasing in the GOR, and some GOR unreported here. Increasing in GOR indicated that we are below the bubble point pressure, less water production here, which is mean no aquifer support, or we have very weak aquifer support here. But what happened in case of increasing above the bubble point pressure? The gas will be increased. What happened? The pressure below the bubble point pressure, we have free gas in the reservoir. Also, we lose the oil mobility. Also, will delay the response of the water injection here. So if you can see here, what is the biggest production, the biggest drop occur in 1950? Because here, as you see here, however, the number of the producer is affected. Okay, because we have a changing in the fluid or the multi-phase fluid flow in your reservoir. The gas come out from the oil. So here, after increasing the GOR here, so you have to start with a pilot. I wanted to inject in your reservoir. This is water flood pilot starting in 1967 here. What is the measurable response of this pilot? Is this pilot is successful or not? Okay, as you see here, the gas oil ratio is going back again, is decreasing, which is indicating that we have a pressure support because we increasing the reservoir pressure. And also which showing after some time here, the oil rate increased. Why? Because we have a pressure support. So the UR is dropped 6 months, uh, is dropped 6 months later. Oil bank is increasing after 1.5 years. Water breakthrough is after 2 years. So we have a response for water injection, yes, but the response is delayed after 6 months and after 1.5 years of injection, showing the impact of the water flooding. Why? It could be due to several reasons, because if we have low permeability reservoir, the permeability is low, which is mean the response of the injection will be delayed. If your reservoir is under voidish, which are you depleting your reservoir more. So this is another way. If the spacing between the injector and the producer is too high, as we have a higher spacing or we have a higher distance between injector and the producer, this could be delay the response of the injector. So all of this point you have to answer. Okay. And after that was showing or the proving success for the water flooding here, we have expanding the your project, expanding the flood expansion and drill another infill wells in order to get the benefit from the reservoir. So here we increasing the oil here, the UR is decreased again, and the number of producer increased here, which is means the reservoir is down spaced. Okay, and we drill another well to get the benefit from the reservoir. But if your reservoir, imagine if your reservoir is not under water flooding here, what do you expect when you drill a well? You expect very, very rapid decline here, but also showing the oil production is steady or increased a little bit. This is related to the water flooding response. So we drill infill. So water flooding leads you to drill infill well, leads you to get to maximize the recovery from the field, and also will order to speed the response, we drill more injector to maximize the benefit from the field. Here you can show we have increased an injection rate. Yes. However, the number of the producer is constant. How? Because we did some work over in your field. So when you are saying this some work over in your field in order to clean up the perforation or get some kind of well work and work over in order to maximize the injection from the reservoir, by then leading to increasing the oil rate. So you have to answer this from the big picture in your field. So you know from this graph we have number of producer is less than the number of injector here, or the number of injector doesn't increase the number of the producer, which is means that we are converting some of the producer to the injector, as this is indication for that. So you have to go to the well and see if you have integrity issue with the completion itself or something like this. So we have converting to injection here. So converting some producer to the injector in order to, as you see can here, number of injector is increased and so on will go your field performance. So you have to show for your reservoir what is the field, what is the healthy water flooding, what is the sequence of operating the field development plan for your reservoir. Another point here, when you are looking for the your reservoir is the secondary primary production. What is mean by secondary primary production here? I mean that we are plotting the cum oil versus oil rate here, and you have this is a primary depletion drive. Why we have cum versus oil? Because you are need to eliminate the shut-in sequence of your fields or the downtime in your reservoir. That's why you are plotting in the cum oil here. For the cum oil, we have primary recovery here. From the primary recovery, we have 94. But due to the water injection, need to maximize or get the benefit from the reservoir. And finally, we have the EUR from the reservoir is about 19.4. So secondary divided by the primary is about 0.957 or around 1, which is meaning your flood. This is rough indication. Your water flooding showing a success for your reservoir. Okay, this is a rough estimation because just to know what is the contribution of water flooding to your reservoir. Also, you have to keep displacement or the recovery factor from your reservoir. How much recovery factor, if your reservoir pressure is maintained, are you achieving the ultimate recovery factor for your reservoir or not? So you have to plot the water injected dividing the recovery factor versus pore volume injected. And as you can see here from the graph, this is analog fields here. And also once you plot here, which showing here start injection at for 7% water recovery, 7% depletion drive. And also if you plot it, we inject around 30% from the pore volume and we get around 12 or 13 recovery factor. So if we applying increasing again, we achieve the ultimate recovery factor. As you can see here, if we inject 100% or 100 or 130 or 1.3, or here we are injected 2.5 pore volume, we increasing the recovery up to 25%. This is our goal. Okay, so you have to compare this with your analog field, where we are and how to get the benefit from this field. Another point when you are designing here for the pressure is your pressure is maintained or not. This is was the objective of VRR and the cumulative voidage replacement ratio. So what is mean by VRR? This is the injection volume divided by the produced volume, and this is to keep your eyes healthy of water flooding. As you can see here at the beginning here, we are injected with high VRR about 5, which lead to premature water breakthrough. As you can see here in the first one, once you inject here, lowering the very premature water breakthrough due to the over injection of the field. So you have to plot this in order to know is your reservoir under voidage or not under voidage. So how do you know if the volume injected at the surface make it to the reservoir? As I said in the first one, by plotting the cumulative field production versus the cumulative injection. Here we have a straight line because we have infill in this reservoir. If we are injecting what we are produced, which is ideal, which is means this a closed pattern and the flow doesn't come across these boundaries. But if we are injecting more than what we are produce, which is mean we have recycling water or we have a safe zone. That's why you have to keep in this mind why we have to safe zone. You have to understand why, and you have to model how to get the benefit and how to maximize the recovery from this point. And if we are produce more than what we are inject, which is mean we have another source of energy, like we have active reservoir. So this is active reservoir. That's as you show this kind of behavior. Okay, this is by the way, this is 45 degrees, like a straight line. Okay. So to take away from the surveillance, this is not only the surveillance, this is surveillance at the field level, but the key takeaway from the field performance rate versus time in order to understand the history of the reservoir, in order to get optimum prediction for your field, and also from the field performance rate versus cube and secondary primary ratio, and the pore volume injected for versus recovery factor, which is indicate for you how the field is behave with our peers. Okay, to boost up this recovery factor from this field, you have to plot this kind of surveillance and to get the maximum from your reservoir. So at the end, thank you for your time, and thank you very much. Any question?
Thank you so much, Engineer Islam, for this interesting webinar and very organized presentation. We will go through the questions that we received in the chat box now. But before this, I would like to encourage you to fill in the feedback form that I will send in the chat now. So we have already received some interesting questions. We have a question, how the capillary pressure affect the efficiency of water flooding?
Okay. The cap pressure is very defined. It affects the flooding from another perspective, from the reservoir characterization here. So the cap pressure, the forces in your reservoir, we have a triangle for forces, which is a viscous force and the cap pressure force and gravity forces from the reservoir. In order to get the optimum, you have to balance between these forces. How to balance between these forces? you have to characterize the reservoir. Characterization of reservoir is based on how to define how many rock types in your reservoir. So from the cap pressure, we can define how many rock type for your reservoir. High cap pressure, which is mean low quality zone. Okay, so low quality or low permeability zone, you have you have to design how to get the benefit from this zone. So we have a special dealing with this kind of reservoir. So for sure it's well impact, but impact in another term is impact on the reservoir characterization, how many rock types you have, how many flow units in your reservoir you have, and how this is the rule of the reservoir characterization and the rule of the reservoir engineer, how to get the benefit from all of this. So is, as I said, this is integration multitask. So you have to integrate this in this model in order to get the benefit. Does this answer your question or no?
I hope it answers the question. Thank you, Zakaria, for your question. We have another question from Dimitri. What do you think about intellectual multi-zonal injection wells? He means working two reservoirs or more.
Sorry,
Intellectual multi-zonal reservoir. I'm thinking that he is asking that he is flooding in two reservoirs at the same time.
yes, for this is the rule of the as I said, this is the role of the petroleum engineer, or is the rule how to get this and the completion design itself. If we have two reservoir at the same time and you have to maximize the production, you could run a dual completion in reservoir, or you have a smart completion, or to get the benefit from the reservoir. How to inject, again, dual completion in reservoir, or dedicate one producers, dedicate some interval for the injection, and drill another injector to dedicate the, how the to dedicate the water to come through this kind of this interval. As I understand from this question, you mean how to handle the multi-layer reservoirs or multi-reservoirs. This is the way to handle by smart completion or design the optimum completion, how to get the benefit by running the two dual completion or smart completion.
Next question. Which is better to use in offshore water flooding, produced water or treated seawater?
This is depend on treated. We are using the same, but treated seawater is we have this and we have this, but this is depend on the compatibility between the injected water and the injected water and the produced water, and the formation itself and the rock itself. So some rock we have sensitive to the treated seawater, and some rock we have sensitive to high salinity. Some the mineral itself should be have compatibility with the mineral and rock itself. If you don't have compatibility, like for example kyanite, this is very sensitive to fresh water. Once we inject the kyanite will spill and will plug the pore root of the reservoir. Plugging the pore root will lose the efficiency of this reservoir. And also in our catalog in the reservoir engineering, no one is the best and the better. The best is to achieve the maximum unit technical cost, whatever. Okay. This is from the technical, you have to have procedures to ensure to get the maximum, and also we have to combine the economics once you propose some program, this kind of program. But we are using the same in offshore. We are using treated seawater, and also we are using the filtered seawater, the produced water.
Another question from Fasih is asking if we are considering only the economic factor, what would be the best flooding pattern?
The best in terms of for which kind?
He is mentioning the economic based on economic level.
Based economic, no one is based on economic. The higher unit technical cost is a better one. If we invest more and we get the maximum, this is could be you have different chart, recovery factor versus pattern. For the pattern X, pattern 5-spot pattern, we achieved the recovery factor 30%. For line drive, we achieved the recovery factor 35%. So what is the best? 35, but 35% costs the company more money. So it's not the best way. So this is based on run economics. No one is better. No one is is good. Yes, no one is the best. So you have to combine the recovery factor, and you have to combine that another one. The factor is the economic factors. So you have to deal with this point. Just going to your model, getting the data, and also we have a chart showing if we applying 5 spot, we have a recovery factor. If we applying this spot, we have another recovery factor. If we applying this, we have another recovery factor. So what is the best economic for this? So you have to answer in this way, not the best or the right. But in case of have low permeability, for sure the peripheral will not impact the injection. If in case we have a high permeability, 5 spot pattern is the best one. If in case you have preferential directional permeability or you have fractures in your reservoir, could be related to line drive reservoir. This depends on your reservoir itself.
Yes, this is more logic. So due to time, this was the last question. Thank you all for attending our webinar. I'd like also to remind you to fill in the feedback form. Thank you for attending the webinar on the basics of water flooding. As we have learned today from Engineer Islam that water flooding is fundamental technique reservoir and petroleum engineering that involves injecting water into an oil reservoir to displace and push the remaining oil towards production wells. This technique has proven to be one of the most effective methods of enhanced oil recovery, extending the life of mature oil fields and boosting their efficiency. I would like to invite you all to our upcoming webinar. I will share my screen. So do you see my screen? So our 65th webinar is going to be a very interesting webinar titled The Use of Different Petrophysical Methods for Improving the Properties in the Static Model with a case study application with our guest speaker, Ana Di Sosa, a senior reservoir geologist. So this will be the next Tuesday, the 18th of April. So I'd like to see you all in this webinar. Uh, Last note, don't forget the feedback form. Thank you, Engineer Islam, again for this interesting webinar and for your time and effort.
Thank you, Sam. I have to play football. Bye bye. Thank you very much.
Yes, yes, you have to get this.
Thank you very much. Thank
Thanks
you.
for your time.
Bye. Bye.
Bye.